Okay, in this section we are looking at the very last item in the D slice, or the random variables and distribution red slice, the central limit theorem. Now it turns out that in statistics the central limit theorem is a lot bigger deal than what it would tend to look like here in ALEC statistics, because really the central limit theorem is one of the central truths of statistics that basically allows everything else that we do in the last slice. All inferential statistics is based on that, and every time I want to tell my students how exciting it is and how important it is, they usually say, well, just tell me how to work the problems and I'll be happy. So that's what I'll do. What we'll do here in this shortcut then is to notice the problem, and this will read very, very closely to a problem that you've already had. Basically, the normal distribution word problems are very close to this, with one important difference. So the main thing is to be able to tell this problem from that one. Here we go. The producer of a weight loss pill advertises that people who use the pill lose after 1 week an average of 1.85 pounds with a standard deviation of 0.95. In a recent study, a group of 50 people, now here's the difference. The difference between this and the normal distribution word problem is that in the situation where you use the central limit theorem, you are always dealing with a sample, always dealing with a sample size. Okay? And so you got to watch for that. There's a very slight difference in the formula, but when you have a sample size, as well as a problem that looks very much like a standard normal distribution word problem, you want to perk up here and think, hey, this is a central limit situation. Now, the study revealed that these people lost a mean of 1.77 pounds after 1 week. If the producer's claim is correct, what is the probability that the mean weight lost after 1 week on this pill, for this random sample of 50, they're saying this again here to emphasize that, will be 1.77 pounds or more? So what we're going to want to do is to set this problem up on one of our normal curve forms and make a few notes as we always do. Okay, I've kind of set up the problem over here on our form as we've done before. Notice here that they're telling us the mean is 1.85, the standard deviation 0.95. We have a sample size of 50. Once again, this is a clue. This is one fact that we don't have on your regular normal distribution word problems. Notice here too then in my form I have labeled up the mean, but I did not label out the standard deviations, because that is the effect of the central limit theorem. It's going to cause that standard deviation to change. The bigger the sample you have, the smaller the actual standard deviation that you're going to use here is going to become. Also, notice that in the past we've had a single x value, one value, one score that we plotted. In this case, notice here that this x bar is actually the average of our 50 individual sample items. So what we're going to do then is to be interested in this area under the curve that is to the right of this 1.77, but we then have a more complicated calculation for the z. But it works so much like what we've done before in the normal distribution word problems that you can do almost exactly the same thing. Just be a little bit cautious down here when you have these stacked fractions. And here we go. So we're going to have the formula that says x bar minus mu. X bar then is this average of the sample, average of the 50, which they tell us here in our story is this 1.77 value. So it says right here, the random sample of 50 individuals will be 1.77. This is their mean weight loss, 1.77 pounds or more. So we plug that in, 1.77 minus mu, which is your 1.85. We're going to divide that first of all by sigma, which is 0.95, but in turn we're going to divide that by the square root of 50. So we're going to have this stacked fraction, and so that takes a little bit of finesse here. It's easy on the ALEX calculator. Let's go plug that in. So on the ALEX calculator, what we're going to do here is to take 1.77 minus 1.85 0.85. Now highlight that entire amount and hit the divide button. I'll put that first line in there for you. Now 0.95, and then divide that, and that'll create that shorter line, thus creating the stacked fraction, the square root of 50, which is our sample size. And we'll just let the calculator burn through all of this nasty math. Our z-score then that we come up with here is negative 0.595. Notice here they want intermediate computations to 4 places, so negative 0.5954. And since that next digit is greater than 5, we'll roll that last digit up, so our z-score will be 0.5955. Now notice then once again that that is a z-score. That is a value down here on the z-axis between 0 and we're going to have 0 and negative 1, so we can see that that z value needs to be negative. And then we're going to want the area under the curve to the right of that. Now once again, we're going to be using the P of Z button, but since that's the area to the right, you must remember that the P of Z button likes the area to the left. So I'm going to store this value and erase 1 minus the P of Z. Keep in mind it likes going to the left, so we'll recall our value here. I'll keep all the digits and then we'll just let it crank. This will get the area on the right hand side that we want, and we find that area to be 0.72. We want this to 3 decimal places, 0.724. Which makes sense because remember here, since our z value turned out to be negative, that this area that we're going to want over here is going to be greater than half, and so the answer must be greater than 0.5. So we should be ready to check this problem and see how we did.